Okay, this is AQA AS Level Physics, Paper 1 from 2024. As per usual, it is streng verboten for me to show the paper on screen, otherwise AQA will get the whole channel deleted like they almost did in the past. So make sure you get the paper to follow along, link in description. Question 1.1. Okay, so we have this chlorine nucleus, just the nucleus, okay, turning into this nucleus. And then an electron as well. So why does it have to be an electron emitted? Well, let's have a look at charge. It's 0. The chlorine nucleus is just a nucleus, so therefore it's just the protons that are going to have charge. So that's 17, and then that goes to 18. So therefore we must have a -1 there. Lepton number, electron-lepton number of a neutrino is just 1. Protons and neutrons just in the nucleus are 0, 0 again, and so it must be +1 again. Well, do we care about baryon number? I don't think we care about baryon number, to be perfectly honest, because it's not that important. So, you know, we've got 37 there, 37 there, so whatever's made as well has to be 0. That checks out. Actually, the mark scheme says treat that as neutral, so we don't, like I was saying, we don't really care about that. So just charge and lepton number, electron-lepton number, it has to be an electron. So we can say charge and electron-lepton number conserved. Okay, 1.2, calculate the specific charge of the argon-37 nucleus. Specific charge is just charge to mass ratio. So that's just charge. Oh, I'll try and make my writing better, fine. And so that's going to be, what are we doing it for? The argon-37. So, it's 18 protons, so that's 18 times 1.6 times 10 to the -19, divided by, I think we can just treat all the nucleons as the same, so 37 times 1.67 times 10 to the -27. Can we cancel out some powers of 10? Why not? I'm going to add -27 onto the top, so that gives us times 10 to the 8. Not that important, but a good idea to get into the habit of doing that kind of thing. And that gives me 4.67 times 10 to the 7. And of course, that's going to be in coulombs per kilogram. But again, we could have gone to 2 sig figs because our data was to a minimum of 2 sig figs. So here we have a Feynman diagram. I hate these now. I don't know why. Electron, neutrino. And then we have, a quark, initial quark, final quark. That's a cool way. Okay, did you see exchange particle and the effect on the baryon? Right, so we have this electron going in, but it's turning into a neutrino, and so therefore we're getting rid of the negative charge. So whatever the exchange particle is, it must be positive. And because it is a weak interaction, well, because it has a charge for starters, it can't be anything else. It's always going to be a W+, W- boson. Let's be honest, folks. It's never really going to be anything else. It must carry positive charge. I'm going to have to make my pen thinner. Might have to. Effect on baryon. Oh, okay. So effect on baryon. Baryon charge decreases or changes. Let's say changes by -1. Because this W+ boson is taking away positive charge, as it were, that means that this quark is probably going to be an up quark turning into a down quark, isn't it? Because that's +2/3 going to -1/3 charge. What else could we say? We could say weak interaction, as leptons are involved. If it's strong, it can't have leptons. And of course, these two here in order for charge to be conserved. Oh, good writing. Look, it's been a while since I've written anything, all right? Give me a break. Okay, 1.4. So we have this argon nucleus decaying into something stable. So, this is just your classic talk about forces in a nucleus. Okay, so first, protons repel each other due to electrostatic force. That's our first bullet point, isn't it? But then we need to talk about attraction as well. So, strong nuclear force acts on all nucleons. It is attractive. This is the thing that people often forget or sometimes forget. It is attractive above 0.5 femtometers. And we can also say range is 3 to 4 femtometers. Repulsive below. What else? Exchange particles associated with these forces. Okay, so weak nuclear force, exchange particles can be W-, W+ or Z0. Strong nuclear force, that is a pion. You might get the answer if you say gluon. Will you get the mark? Yes, condone gluons. There we go. We used to say gluons, now we say pions. Who knows why? It's because, well, all this is made up, isn't it? Let's be honest. Okay, the role of these forces in keeping the nucleus stable. So when a nucleus is stable, the repulsion, or let's say repulsive forces, or repulsive and attractive forces between nucleons are balanced. Question 2. Tube contains a vapor of mercury atoms. Vapor is bombarded. Fine. Electron in the beam gains. I'm going to put kinetic energy here. EK equals 6.7 electron volts. Are we going to turn that into joules? Let's leave that for a second and see what the question's asking us. By moving through a potential difference V. Now, this is a question that they're asking because this is a thing that a lot of students just don't understand. Electron volts. It literally just tells you how many volts an electron has been accelerated through. That's the whole point of this unit existing to begin with. Okay, and we know that because the conversion factor is E itself. So therefore, accelerated through 6.7 volts. Easy as that. So if you know the electron volts of an electron, or it could be a proton as well, for that matter, same magnitude of the charge, then the PD that it's been accelerated through is just the same number. Electron collides with a mercury atom, blah, 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 blah. Calculate the wavelength. Oh, okay, right. So we do need to turn that into joules now. So our conversion factor, of course, is 1.6 times 10 to the minus 19. Are we going to be multiplying or dividing? Well, we know we want a small number because joules are bigger. So we're going to be multiplying by 1.6 times 10 to the minus 19. So 1.02 times 10 to the minus 18 joules. Okay, so we know that E equals HF, but we're looking for the wavelength. So, well, we know that V or C, let's put C because we are talking about the speed of light. So we can see that F is equal to C over lambda. Popping that back in here, you know this already, hopefully, anyway. So energy is equal to HC over lambda. We're looking for lambda. We have the energy, so we're going to swap these two bad boys round, and we're left with lambda is equal to HC over E. So that's Planck's constant. Oh, that wasn't very good, was it? Times by 3 times 10 to the 8, divided by the energy, that's 1.07 times 10 to the minus 18. Let's sort out some powers of 10, why not? So plus 18 on top, so that is going to be now minus, oh man, bad maths, minus 16, and then times by 8 as well, so this just ends up being ultimately minus 8. Of course, you don't have to do that, but like I said, it is a good thing to get into doing because it can rear its head in multiple choice questions. So that gives us 1.86 times 10 to the minus 7 meters. Again, we could have gone to 2 sig figs, but as a rule of thumb, you'll get the mark if you go to 3. Really, the only place you'll get marked down for that is in the practical skills papers. Okay, we have energy levels. So minus 3.16 electron volts, minus 4.96, and minus 21.56. So we're talking about n equals 0. Oh, flip, they're just calling them A and B. Whatever. Okay, when an electron collides, so we're talking 18.4 electron volts of energy is transferred to the atom. The atom subsequently. Okay, so obviously, oh, actually, can I do maths? Okay, let's have a look. 21.56 minus 3.16. Hopefully, that's going to give us 18.4, and I'm pretty sure it is. So that is our energy change. So when this electron collides, it goes up to there. But then we're told that the atom subsequently emits a photon of visible light. State and explain the energy transitions that are involved. Support your answer with appropriate calculations. So we can say electron is excited to energy level B. I've already done the calculation. Can emit 3 different wavelengths as it de-excites, of course, because it doesn't have to go straight down to the ground state. So yes, it can do that, but also it can do that, then that, and all 3 of these emit a different wavelength. So we're looking for a visible light wavelength being emitted. So I guess we're going to do this whole lambda equals hc over e again. That's a little bit annoying, isn't it? Do we have to do that? Yeah, I think we're going to have to. Well, I'll tell you what, let's do it for b to 0 first. And so that's 6.63 times 10 to the minus 34. This seems like a lot of work, so I'm not really happy with this question, I have to be honest. So we're going to say 18.4, but then we're going to multiply that by our conversion factor because we need it in joules, don't we? Okay, so that gives us 6.8 times 10 to the minus 8 meters, because visible light, we're looking from, say, 400 nanometers to 700 nanometers. Yeah, let's do this one here, shall we? So 4.96, so difference in energy equals 4.96, take away, what was it, 3.16? Oh my days, come on. And that gives me, what's that, 1.8 electron volts. So doing the same thing again, so lambda is equal to, I'm just going to go for this again, so that times that. And we should end up, this is looking kind of good actually, so I think we're on to a winner here, boys. And that does give us 6.9 times 10 to the minus 7 meters, which is 690 nanometers. That seems pretty good to me. The other one here, as well, that's going to be 21 to, or 4.96 to 21.56. I can see that, you know, that's not too different from, because, okay, so this energy level should really be somewhere like there. So they've drawn the energy diagram a little bit cheekily, if you ask me. Yes, to try and throw us off. But we are going to be better than them. So yes, I think that's going to be too big as well. If you want to prove it to yourself, you can do 21.56 take away 4.96. Okay, it's a bit of waves. We have a guitar and the distance xy is, okay, so I'm going to put that in meters before we start. Frequency of the first harmonic is 147 hertz. Calculate the speed of the wave traveling along the string with pleasure. If it's the first harmonic, then we're talking that, aren't we? So that means that. So that means that we have half a wavelength on the string. So that's lambda over 2. So therefore, lambda is two lots of the length of the string. And so if we're looking for V equals F lambda or C equals F lambda, that's going to be 147 times by, I'm just going to say 2 times 0.648. And that gives us 191 meters per second. Tension of the string is 71 newtons. That's not time period, that's tension. Calculate the mass of the string between X and Y. Okay, so we need our funky equation, 1 over 2L root T over mu. We're looking for mu, so let's square the whole darn thing. So we end up with 4L squared there, times by T over mu. We can get rid of that, can't we? And we're looking for mu, yeah, so we're just going to swap those two over. So therefore, mu is equal to T over 4L squared F squared. And, well, let's just find that out first, shall we? So 71 divided by 4 times 0.648 squared times by 147 squared. And that gives us, well, I'm going to say that's 1.96 times 10 to the minus 3 kilograms per meter, because of course that's what mu is. So we could just say, oh yeah, we'd just be in asked kilograms, so that's fine. So that's per meter, but the problem is that we want just kilograms. So units are your friends here. So we have kilograms per meter. We just want meters, so we need to get rid of the per meters. We're going to do that, of course, by just multiplying by that 0.648. And that gives us 1.27 times 10 to the minus 3 kilograms. Okay, we have the harmonics. I love all this stuff. Sound is incredible. All right. Draw on figure 5 the stationary wave that produces the harmonic F3. Okay, F3 is just the third harmonic. And hopefully you should know that the number of the harmonic gives you the number of loops on the piece of string. So there's our string. Not very straight, but we have 1 loop, 2 loops, 3 loops. Whoops, not very even. You can make them a little bit evener. it's always a good idea to draw the opposite version as well with a dotted line. You don't have to, but it makes it easy to see, you know, how many loops you have and all that jazz. So that is 3.3. Okay. Oh, we've been asked to label nodes and antinodes. Of course, nodes in the middle, antinodes. That's easy. 3.4. Strings vibrating freely. We're doing harmonics. You know, like bing, like very. Who's that band? What are they called? Ah, that's going to do my head in. Somebody told me, I'll be your roundabout. They like their harmonics. Anyway, concentrate. The sections X, Y, blah, 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 blah. Deduced with reference to frequency how harmonics present in the sound compare with the harmonics present in figure 4. So, by pressing finger... do you know what? I'm really liking this paper so far. Node is forced there. Therefore, antinode cannot be produced. Therefore, only F2, F4, etc. can be produced on the string. Can't even have the fundamental. And that's why you hear that bing as opposed to that bong. Evenly numbered harmonics, i.e. evenly numbered harmonics. Cool. 4.1, we have a car and it's going at... Okay, fine. So we're going to... this is Suvat, in it, because we have acceleration. If we have acceleration, bet your bottom dollar it's going to be Suvat. So U is 25 meters per second. Does it come to a standstill? Stop at the lights. Yep. So V is going to be 0 meters per second. Constant deceleration of, we're going to say minus 2.8 meters per second squared. It is important whether it's a positive or a negative. We don't care about time. Being asked what the distance is. So therefore we're going to say V squared equals U squared plus 2AS. Let's move U squared to the other side. Let's do it one step at a time. And of course, V squared is 0. And then we just need to get 2A to the other side. So we can just cross those out over 2A. So therefore, S is equal to minus U squared. So that's minus 25 squared divided by 2 times minus 2.8. Minuses disappear because of course they do. That seems like a long... Oh, okay. It's not an emergency stop. So we end up with 112 meters. 4.2. Initially there are... Oh, wait. What have we got? Oh, it's one of these. Oh, man. Don't take the mick out of my cars, please. Oh, no. Okay, you can take the mick out of that one. That sucks. So we have this force there. I'm going to put that in blue. Oh, whatever. Let's draw the trailer first. Boop. Boop. Look, I'm in a hurry, all right? Oh, what is going on with this question? Okay, we have pH there. Is this a moments question as well? Yowzers, this will be pretty crazy. And then upwards R there, reaction force. Woo, boy. Okay, initially there are no resistive forces and the trailer accelerates at 1.5 meters per second. Right, okay. Okay, these questions are pretty hard. Calculate the initial value of pH. Now, we've got to remember that F is equal to MA, but we know that, don't we? But it's good to remember what do these actually mean. And it's good to remember that this is the resultant force. That's not that important in this case, so I'm not really fussed about that. M is the mass being accelerated, and then A is just the acceleration, all right? So in essence, it doesn't matter what's going on with the car because the trailer is being accelerated at this acceleration. We want to know what the force on it is. It doesn't matter what is producing that force. We just want to know what that force is, all right? So pH, I guess, therefore pH is equal to mass times acceleration, but we have weight here, so we're going to say that that is weight divided by G. All right, we're going to divide that by G to turn it into grams, aren't we? Times by A. So that is 2,500 times by the acceleration, so 1.5, divided by 9.81, and that seems to give us 382 newtons. If you're going to 2 sig figs, of course, that would be 380, wouldn't it? Now, what are we being asked? Well, we've got a graph here. Oh, my days. I hate it when there's a whole page without a question because there's so much information. Okay. Drag. Okay, we're talking about drag. Right. So, boop, boop. V drag. Okay. Figure tension is the forces on the trailer when it's traveling constant horizontal velocity. Okay. Car exerts a force PV. What is it? Oh, because it's going to tip over? Oh, I don't know. Oh my days. Okay, I was liking this paper. Now I'm not. The horizontal force pH is now greater than the value calculated in 4.2. PV 762 newtons. pH. Oh, sorry, the resultant. Oh, okay. Right. So we have this. Okay, let's do it one step at a time. That's pH and that's PV. That's going to be 762 newtons. The resultant is 912. So therefore we can do reverse Pythagoras to get pH, can't we? So pH is going to be equal to the square root of 912 squared take away 762 squared. So I've got pH as 501 newtons. All right, determine V1. And what is V1? The horizontal velocity. Right. Oh, okay, so we do actually need that. Right. So therefore, if it's traveling at a constant velocity, that means that drag force is also equal to this 501 newtons. There we go. Now let's look at our graph. 500, let's just go for 500, and that is bang on 10 meters per second. Therefore, V1 is equal to 10 meters per second. Ugh, what a weird question. 4.4, explain why pH has no moment about the center of the trailer's wheel in figure 11. Well, that's easy. Well, that is because pH, or direction of pH, is acting along... how do I put this? Because we know a moment is force times, the technical way of putting it, force times distance perpendicular to force's line of action. So there we go. We can say pH is acting along perpendicular distance to pivot. There we go. That's the way we can put it. In other words, there is no perpendicular component to pH in order to provide a moment. Perpendicular distance to pivot, which is the wheel in this case. 4.5, when the car and trailer travel with velocity 2, PV is 0. Determine V2. Oh, my days. All right, so PV is 0. So PV is 0. Therefore, it's going to be the drag is going to change, isn't it? So there's our wheel. Oh, actually, hang on. There we go. There's our wheel. And then there's our reaction force. Do we care about that? No, because we're going to be taking moments about there. So we don't care about that. So So I'm just going to do that. I'm just going to... I tell you what, actually, I changed my mind. I'm going to do that with a solid line. That there is 2,500 newtons. The distance to the pivot, to the wheel, is 0.8 meters. So there we go. We can find out that moment due to the trailer's weight. And then we know that the drag force acts up here. Okay, that's not too bad. That's not too bad. So even though they're at funky angles, well, not at funky angles, they're just right angles to each other, the whole clockwise, anti-clockwise thing still works. So we're going to do that. And then we're going to just have the drag force going along there. So if this is the case, therefore, moment due to D equals moment due to weight. So if they're equal, then there doesn't need to be a moment due to PV. So there we go. So we can just say 2,500 times by 0.8 is equal to 0.95 D. Those are our two moments. So therefore just divide that by 0.95. So therefore D is equal to 2,100. And so going back up to our graph, 2,100. And luckily enough, they've given us a nice number there. So V2 is equal to not 21, but 20.5 meters per second. There we go. Okay, 4.6. Blah, blah, blah. There is resistance in D. Explain this increase in drag with reference to the momentum of air displaced. They love asking this kind of question these days about air particles and momentum. It's so dumb. It's so pointless. We know why this happens. Oh. Whatever. So as V increases, more momentum given or imparted to air particles. We could say every second because, well, we know that F is equal to delta mv over T. And so if it's every second, that takes care of that. So therefore, force exerted by air particles on trailer equal and opposite force due to Newton's third law. There we go. Whatever. 4.7. Car has a maximum power output of 95 kilowatts. Maximum velocity, I know this is going to be P equals FV already because, you know, power and forces is always going to be that. So even before we start, let's write that down. That's just a reworking of work done equals force times distance, of course. It's just that equation divided by time. So we're probably going to use that. Let's have a look. Maximum velocity of the trailer car is that. Drag force is, I'm just going to put F is equal to that. Car exerts a horizontal force P on the trailer. Oh, that's the car. Oh, okay. Car. Okay. And force D on the trailer. That's the important thing that we have to consider, I think. Is it? I don't know. Car exerts a horizontal force PH on the trailer, and the trailer exerts an equal and opposite force of magnitude PH on the car. Yeah, at the door. Assume that air resistance. Calculate the air resistance acting on a car when it is traveling at a constant velocity of 25 meters per second. Okay, so the first thing we need to do is go back to our graph all the way back. So 25 gets us to 3,000. What is the point in telling us that then if you're just going to give us the drag force already? Oh my days, I'm starting to lose at AQA. Right, so we don't care about that. Yeah, we literally don't need that. So the drag force is 3,100. Okay, unless we need that for the car. Yes, we do. Yes, we do. Yes, we do. Yes, we do. Right. So we do need that. The power, this needs to overcome, as it were, drag force on car and trailer. I think that's what we need to consider. Air resistance and pH are the only resistive forces acting on the car. Right. Okay, got it. So this is P total. So therefore, we're going to say P total equals FV. So therefore, F, and that's going to be the total resistive force, the total resistive drag, whatever. So therefore, F total is going to be equal to this P total, the total power divided by V. So that's going to be 9.5 times 10 to the 4 divided by 25. And that gives us 3,800 newtons. That's the total force supplied by the car. Sorry, that's what I should say. If it's traveling at a constant velocity, then of course, 3,100 newtons of that is due to the trailer. Therefore, it's just going to be 700 newtons drag on car. So we do have to separate them out a bit. There we go. Again, not super easy to get your head around that. 5.1, we have a circuit. It's worth me drawing this. Maybe. L1. Okay, we have this graph of resistance against I. Okay, and oh no, don't tell us. No, we're not going to be counting squares. That doesn't make sense. Okay, the current is increased from 0 to 0.5 amps. So therefore the resistance doesn't change according to the graph. The potential difference across V, I'm just going to say V1 equals 0.375 volts when I is 0.5 amps. Draw a VI graph for L1 in the range. I'm a little bit confused about this one. I've got to be honest, folks. So, okay, let's have a think about this. When there's no PD, there cannot be any current flowing. That makes sense for starters. So we know it has to start at 0, don't we? So when the PD is that, I is that. Okay, so it just goes to there like that. Okay, fine. You can see that the resistance of the lamp doesn't change from 0 to 0.5 amps from the first graph from figure 13. So therefore, if the resistance doesn't change, so R doesn't change, resistance of the lamp doesn't change, therefore it's acting like just a normal resistor for these PDs and currents up to 0.5. Therefore, ohmic, what do we know about an ohmic conductor? Well, it's a straight line. So from 0 to 0.5 amps, it is acting like a normal ohmic resistor, like we said, right? Bit of a weird question, that one there. Okay, 5.2, calculate the power dissipated in L1. So power in the lamp, well, power we know is either IV or I squared R or V squared over R. It just depends on what numbers we have. So I is 1.9 amps. And we don't know the PD, of course. So therefore, well, I mean, we could kind of figure it out, but we're not going to do that. We might as well just use the resistance. Oh, wait a minute, 1.9 amps. Okay, so we are going to have to go all the way up to there. So looking at figure 13, that is 3.6 ohms, looking at the graph. So we have I and R, so we're going to use I squared R. So therefore, power is going to be equal to 1.9 squared times 3.6. And that gives us 12.996, so we can just say 13 or 13.0 watts. 5.3, the variable resistor is adjusted until I is 1.5 amps and V is 3.3 amps. Calculate the resistance of R. Okay. What? Oh, V. Wait, what? V is... Oh, V is across the lamp. Sorry. Therefore, because they're in series, of course, that means that the PD across the resistor is going to be 9 take away 3.3. So that is 5.7 volts. And then we can just use V equals IR. Therefore, resistance is equal to V over I. So that is 5.7 divided by 1.5. Again, same current because they are in series. And that gives us 3.8 ohms. I wish they would have put a subscript L there, but that's just me. Okay, I guess I forgot to do this one first time around. So question 5.4. And so we have this circuit going on, 2 lamps. We're told that R is changed, so PD across L1. So that just means across both of these is going to be 3.3 volts. So that means that the PD across here, the variable resistor now, R, is going to be 9 take away that. So that's 5.7 volts. Deduce without calculation the change in the resistance of R. Oh, so without calculation, fine. Well, we now have 2 lamps in parallel. I'd be tempted to say that the resistance of 2 bulbs in parallel is half that of just one of them, but that's not the case. That would be the case for fixed resistors, but not for lamps because, of course, it's going to be a different current flowing through them. So, yeah, we can't really say that. So I think it's just going to, it says deduce the change. That implies that we're actually looking for a number. So there's a really dumb and mean question yet again. It should just say, describe how R needs to change. That's what it should say. So we know that resistance of 2 lamps in parallel, less than 1, not going to be half though. Therefore, R also needs to decrease by same proportion. So let's say, for instance, that the resistance of L1 and L2 is half what it was earlier with just one of them, then that must mean that R must also half in order for the ratio of the PDs to be the same, because of course we know that V1 over V2 is equal to R1 over R2 for things in series for a potential divider. In this case, that would be VR. R, whatever, we don't need that bit, and then of the lamps as well. So yeah, it's as simple as that. We can't, without calculation, so nothing really else we can say. 6, we have a bungee jumper. That's quite classic. Experiences free fall when he steps off the platform. Okay, during which part of the jump does the boy's acceleration begin to decrease? Okay, so let's have a think about this. So, bit of a weird question, this one, because it's V against S. At the top is when V starts going down again. So, because his velocity is getting lower as his velocity is now getting slower as he's going down. It's not quite that simple, I don't think. So it must be before, therefore must be before, what's that, 15 meters. I'm going to say that it's 7.5 to 15 meters. So because it's no longer free fall, but the speed is still going up, but the acceleration is getting less. Let's have a quick look, shall we? So let's put it this way. Let's use SUVAT real quick. So V squared equals U squared plus 2AS. Let's just check what should, if free fall, what should V be at 7.5 meters, let's say. So we go V is equal to the square root of 2AS. So that's equal to 2 times 9.8. This is what it would be if it's free fall. We're checking it. times by 7.5. And that gives us 12, pretty much 12 meters per second. So let's just check. At 7.5 meters, yes, it is 12 meters per second. So therefore, we've just proven that, well, we can assume then from 0 to 7.5, he's still accelerating under freefall. And then if we do the same for 15, we'll find that that isn't the case anymore. It's not going to be right. Should we prove it real quick? V is equal to 15 meters, question mark. So 2 times 9.81 times by 15. And that gives us 17.2 meters per second. If we have a look on the graph for 15 meters, we can see it's nowhere near that 17.2. So it's already started to not decelerate, but the acceleration has started to come down. So it is in between that 7.5 meters and 15 meters. There we go. Not an easy question though, but it's this whole V against S. In that case, if you've got a graph of V against S, or it could be A against S as well, then crack out your Suvat equations and check some values. 6.2, when the boy's central mass, 6.2, we have distance of 15 meters, GPE, so difference in energy, EGP, let's say, is 9,560 joules. Calculate the mass of the boy. Okay. So this is a year 9 question, it appears. So we're going to say H is 15 meters. So therefore, change in EGP, GP or whatever is mgh. So therefore, M is equal to, I'm just going to put E divided by GH. So that is our energy divided by 9.01 times by 15. And that gives us 65 kilograms, which sounds about right. Not for me, but for a boy, I'm sure. Okay, springs now. K is 110 units per meter. Kinetic energy is 7.7, let's put it 7,710 joules. Calculate the extension of the rope, right. Would you humor me if I call that X instead? Much easier to deal with, in my opinion. Okay, so we're being asked for the delta L when the kinetic energy of the buoy is at a maximum. So at max EK, so therefore V max as well. And looking at the graph right at the start, we know that's at 15 meters. But it's a little bit more complicated than that. Well, it's not more complicated. The point is that the buoy still has kinetic energy. So how much energy has gone into the spring? We know from the previous question that the GP lost is that much. And so we can say at top, just GPE, EGP, whatever. Oh, let's call it GPE. Everybody calls it GPE. And then at 15 meters, no GPE. Yes, okay, there is, but we're talking about this height of 15 meters. So we're going to say all of that GPE has now gone to somewhere else. It's gone to KE and spring energy. So therefore, we can say that, well, the GPE is equal to, that's fine, just KE plus energy in the spring. Or we can say, therefore, GPE minus KE is equal to the energy in the spring. That's what we're looking for. I've not set it out very well, but the important thing is just, hey, we had this much total energy to begin with. It's being shared between KE and spring energy by the time we reach 15 meters, and we just want to find the difference. That's all. And so therefore we can say that E, I'm just going to call that E, I'm just going to, yeah, there we go, is equal to that 9,560, take away that kinetic energy. What does that give us? 1,850 joules. And well, now we need the equation for spring energy. That's E equals half K, well, you could say delta L squared. I like using X squared. So therefore, rearranging this, let's do it one step at a time. So 2E over K is equal to X squared. So therefore, X is equal to the square root of, that's supposed to be a K. That's square root of 2E over K. So that is equal to square root of 2 times 1,850 divided by that 110, that spring constant, What does that give us? 5.8 meters. There we go. 6.4, deduce the tension in the rope when the kinetic energy of the body is at a maximum. Give a reason to support your answer. Okay. So, tension in the rope. So, of course, this is going to be... okay, hang on a minute. Look, we've got the energy stored, haven't we? That's easy. So, we have the extension and the energy stored. Look. So, we just need our other energy equation. E is equal to half delta L, or half Fx. So, therefore, the force is going to be equal to 2E over X. So, that is 2 times that, 1,850 divided by 5.8. And that's 638 newtons. Why are we being given a reason for our answer? Why are we having to give a reason? I don't really understand that. It's obeying Hooke's law, so that's going to be the case. We could have also just used F equals Kx, F equals K delta L, of course, the DOI. Making life hard for myself. The mark scheme says some nonsense about idea the resultant force acceleration is upwards for tension greater than this value. That makes no sense. We don't care about that. Yeah, as it obeys Hooke's law. I mean, that's the whole premise of this question. That's possibly the stupidest question I've seen in a very, very long time. Bad AQA. 6.5. We're talking about proportionality. Nice. So why wouldn't they give us the actual symbol form? That's so dumb. Ugh. KL over A. Okay, show that each rope has the same stiffness. Right. So rearranging this, K is equal to EA over L. And so therefore all we have to do is just do K1, relatively speaking, is proportional to 1, because it's just E times by 1, because it's A divided by 1. So it's 1, all right? So K1 has a value of 1. That makes sense. K, therefore, is proportional to 1.2 times by 1 again. Don't care about that. Divide by 1.2. And so therefore, that's equal to 1 as well. Ugh, dumb question. 6.6. Deduce whether the buoy's maximum velocity is increased when using the second rope. Okay, so they have the same. So they have the same K, but second rope has longer original length or initial length. Therefore, if it's longer, this isn't an easy question again. Buoy will accelerate for longer time before reaching length of rope, and therefore a acceleration decrease, therefore max EK greater. Man, this paper started off so well. Game of 2 halves, wasn't it? First half, thought we had them. Second half, went off the rails a little bit, but there we go. Right, hope you found that helpful. If you did, leave a like, leave a comment. See you for paper 2. Bye for now.